Hello.
Good afternoon.
I have a video.
Question, Mr. Chartier, are we supposed to send you pictures of our assignments through Microsoft Teams?
Affirmative.
Okay.
We have one member not present.
Jack did say he might not be here.
Okay, I'll get started then. Oh, got something to show you guys. So, geometry book, right? Actually, that's the teacher edition. Student edition.
Did you get the PlayStation 5?
Oh, I tried. Oh boy, did I try, and I had to teach too, so I couldn't. At 1 o'clock was my best opportunity. Nope, I failed.
Okay.
All right.
What do you want to show us?
Geometry book, right? Next book, next year book. All right. Pre-calculus. Literally, this is the difference in pre-calculus, geometry. It's that much bigger. It has.
That's the size of our biology textbook.
Oh no, math is going to be bigger than science. I made sure we bought one that was bigger, just to show up the science people.
Oh boy.
It has a lot of pages in the appendix, but I don't know if you can see that. Page 925. A lot of pages. And that's just one of two books. Anyway. Okay, let's get going. Questions on the homework? Nothing? All right, I'll call out the answers. What are we on? Page 210. 210. All right, here we go. 1 through. Oh, I'm on the wrong. Oh, that's right. 6-2, page 210. There we go.
210 and 211.
Yeah, I got it. All right. So let's see. 1 through 15 all. So number 1 had a part A, part B. A was the contrapositive. B was the inverse. So the contrapositive is if 4n does not equal 68, then n does not equal 17. And the inverse would be if n does not equal 17, then 4n does not equal 68. Number 2, contrapositive. If this is not blue, then those are not red or white. And the inverse, if those are not red and white, then this is not blue. Number 3, contrapositive. If x plus 1 is odd, then x is even. And the inverse, if x is even, then x plus 1 is odd. Number 4, contrapositive. If Abby is well, then she is here. And inverse, if Abby is here, then she is well. On the table, I'm just going to call out the true false part of it. Number 5 would be true, true, false, false. Number 6 would be true, true, false, false. Number 7 would be false, false, true, true. Number 8 would be all true, everything's true. Number 9 would be true, 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 true. And number 10 would be false, false, true, true. All right, 11 and 12, they wanted you to make a Venn diagram. I will just call out the answers to A, B, C, and D. A would be no conclusion. B would be she's at least 30 years old. C would be no conclusion. And D would be he is not a senator. 12A, let's see, she assigns hours of homework. B would be no conclusion. C would be he's not a math teacher. And D would be no conclusion. All right, 13. There's an A, B, C, and D. A is it is raining. B is I am happy. C is no conclusion. And D is no conclusion. Two left. 14A is he loves geometry. B is no conclusion. C is no conclusion. And D is he is not my student. 15A is no conclusion. B would be angle ABC and angle ADF, or DBF, sorry. C would be no conclusion. Sorry, I call it the wrong answer for B. B should be angles ABC and angles DBF are not vertical angles. And then D, delta would be angle RVU is congruent to angle SVT, and angle RVT is congruent to angle SVU. And that was it. 1 through 15 all. Questions?
Did you go over 13 through 15 again?
Sure. All right, number 13. It is raining is A. B is I am happy. C is no conclusion. And D is no conclusion. 14A is he loves geometry. B is no conclusion. C is no conclusion. And D is he is not my student. That was 13 and 14. Good?
What about 15?
15, A is no conclusion. B is angle ABC and angle DBF are not vertical angles. C is no conclusion. And D is angle RVU is congruent to angle SVT, and angle RVT is congruent to angle SVU. And that's it. All right. Let's see. Quiz tomorrow. I'll talk about it here at the end of class. Oh, I can talk about it now. So the quiz is going to be just, can you write a converse, inverse, and contrapositive, and can you make, can you figure out whether things are true or false based upon those statements? All right, here's your homework for tonight. Brand new stuff tonight. You have never done this stuff before. All right, so we're going to do something called an indirect proof. It's also in most books called proof by contradiction. Indirect proofs. So far, up until today, when we've done a proof, we've done nothing but what's called a direct proof. Now, I'm not talking about the type of how you write the proof. Remember, we have a couple types. We have a 2-column proof. We have a paragraph proof. We have a one that we've talked about where we've actually drawn pictures to do the proof. But this is an actual different logical way of proving something directly. And today we're going to learn the indirect method, also called proof by contradiction. All right, so let's first define what a contradiction is. A contradiction is a combination of statements, like more than one, or ideas, or features of a situation that are opposed to one another. So for instance, if I make the statement, I like to eat healthy, and I only eat Oreos, those two statements contradict each other, because I think we would all agree that if all you ate were Oreos, that would not be healthy. So we're talking about statements when you make a contradiction that have two opposing points of view, or two that do not align with each other. And that's called a contradiction. Today we'll be using contradictions to arrive at a logical conclusion. So up till now, the proofs that we've done, for instance, if I wanted to prove that two even numbers, if you add them together, you get another even number, well, I would have to prove that directly, called a direct proof. Now, we do now have two different ways of doing that. We simply prove the statement itself, Or we learned yesterday that if we prove the contrapositive, that's also good enough to prove it. Those are called direct proofs. Well, we have a second method of proving something called a indirect proof. And an indirect proof does this. It assumes the opposite of the conclusion. So for instance, if our statement is if you have two even numbers, that their sum is even, it assumes the opposite is true. That if you have two even numbers, that their sum is odd. So it takes that, clearly a false statement, it takes that false statement, and what it does is it applies it to some logical statements. And in what happens is you arrive at some contradiction of the facts. And as soon as you arrive at that contradiction, then that's how you make the conclusion, well, therefore their sum can't be odd, they must be even. So, I mean, that's the gist of it. And I know that when I talk about it using words, it's kind of hard to really wrap your head around it. You kind of got to see an example. So I think I have 3 examples here. This is all we're doing today is just proof by contradictions or indirect proofs to show you how this works. All right, so once again, in an indirect proof, we take the final statement here that their sum is even, and we negate that, or we consider the opposite of it, and we show that this would arrive at some faulty conclusion that contradicts a previous statement, and therefore, if that's true, then our initial assumption that their sum is odd must be false. Okay, it leads to this contradiction. All right. So most kids won't get that from that explanation. They actually have to see an example. So I'll define an indirect proof formally here. So that's a proof where you temporarily assume that the conclusion, the desired conclusion, is not true. You temporarily assume that, and then you prove that this would lead to some contradiction. And you're like, what contradiction? Yeah, that's the elegantness of this proof, is that it leads to some contradiction. This is also called a proof by contradiction. Okay, so that's what an indirect proof is. If you were, I would have had you written down this on a paper. Doesn't necessarily have to go in a book of truth. What needs to go in the book of truth is these 3 steps. So these are the 3 steps and you won't find this in the book. It doesn't really spell it out, but these are how you do an indirect proof. So step number 1 is you assume that the conclusion is not true. So you rewrite the conclusion, and that's the prove part of the proof, so that it's not true. So for instance, if it's proved that this angle is congruent to this other angle, well, then you write the opposite. You say that this angle is not congruent to this angle. You take that as a fact temporarily, and you show that because of this, you get to some logical fallacy. In other words, you get to some conclusion that cannot possibly be true. So for instance, let's say you assume that this is congruent to this, and that leads you to find that triangles have 4 sides. Well, clearly that's not true. Therefore, your initial assumption must be false. So step 2 is you continue to reason logically. This is the hardest part. Until you reach a contradiction of some known fact, either a theorem or a definition or a postulate. Step number 3 is kind of how you finish the proof, is you point out that your temporary assumption therefore must be false, and therefore your conclusion of what you were trying to prove must be true. And once again, as I read this makes perfect sense. I know the first time that I was exposed to an indirect proof, I was like, what in the world is going on? I don't get it. But as soon as I saw an example of it, I got it. It's pretty easy concept once you see a couple of examples. So I'll go ahead and pause and allow you to write this all down. The other thing that I would put in your book of truth is I'm going to show you 3 examples here. Pick the one that you like the most and put it in your book of truth. And remember, I'll post the video between now and 4 o'clock, and then you can just replay the video and write the proof. So that's in your book of truth. So eventually, if we were on a test and I say, and by the way, this chapter I'll say do a proof by contradiction. At least you'll have an example. Step 2 is the hardest one, though. It just basically says you got to reason logically. What the heck does that mean? You basically, call up some facts, and these facts lead to some contradiction. Like I said, the easy example would be You assume something, and this assumption causes you to reach the conclusion that triangles have 4 sides, and that would contradict the fact that the definition of a triangle states that it has 3 sides. Proof by contradiction works well when there's only 2 choices. So for instance, odd or even, or true or false, or congruent or not congruent. That's when proof by contradiction works well. All right, we ready to move on?
Yes.
Yes.
Okay, here we go. So I usually, and this is an example I give in class, it's not a proof, but I say, imagine me standing in front of you, and I claim that my pants only have 2 pockets, a left one and a right one. There's just 2 pockets. And I will guarantee you that there is a dollar bill in one of my pockets. And what my proof would be is I want you to prove that the dollar bill is in my right pocket. So a proof by contradiction would start off by assuming the proof part is wrong. So instead of proving that the dollar bill is in my right pocket, I'm going to assume temporarily that the dollar bill is in my left pocket. Now remember, I'm trying to prove that it's in my right pocket. So I'm going to assume that the dollar bill is in my left pocket. So step number 1 in the proof after the given is assume that the dollar bill is in my left pocket. Then what I would do is I would show you what's in my left pocket. Well, clearly the dollar bill is in my right pocket. That's what I'm trying to prove. So when I empty my left pocket, right, you find out that it's empty, and that would contradict the fact that we just made the assumption that the dollar bill is in my left pocket. So since I just contradicted myself, and there's only 2 choices, either left or right, and since it's not in my left, it must be in my right. So there's a quick and easy example of a proof by contradiction. So in geometry, why would we choose to use a proof by contradiction? Well, we choose to use it generally when we can't prove what we're asked to prove. We're given a proof, we try to prove it directly, we find out, man, this is just too hard, I can't do this. So then what you do is you switch gears and you say, well, maybe I could prove this easily or more easily by a proof by contradiction. And I will just say throughout this book, I will point out when you should probably use a proof by contradiction. The examples I'm going to give you today could be proved either way. I don't have a solidly, because I want to save those. I don't have a solidly good example of one where you must use a proof by contradiction, but I will solve all the proofs today by a proof by contradiction. Okay, so think about this. We're about to do a proof here, but I got to set this up first. What's an even number? Well, those are examples of even numbers. So what's an even number, somebody?
A multiple of 2.
Right? Any number that's a multiple of 2, or any number that's divisible by 2. So mathematicians have decided they would like to write the definition of an even number as not using division, a number divisible by 2, but they would rather the definition that you just gave me, a multiple of 2. So this is how a mathematician would write what is an even number. They would say it's a number defined as 2 times some integer k. So in other words, k can be any integer, can't be a decimal number, right? It has to be an integer, both positive or negative, right? 0 is an integer as well. So 2 times 3, for instance, let k equals 3 is 6, and 6 is an even number. 2 times 14 is 28, 28 is an even number. 2 times 0 is 0, so therefore 0 is an even number. So I'm going to define all even numbers as 2 times an integer, let's call it k. Okay, so that's how I'm going to define an even number. So now let's do a proof. So here's the proof that I'm trying to prove. I'm trying to prove that if you take 2 even numbers and you add them together, that the result is even. Okay, so this is a perfect one to solve for proof by contradiction. So here's how a proof by contradiction is done. First off, it looks just like a normal proof, right? I'm going to do a 2-column proof. You can do a paragraph proof as well too. The difference is what follows next after the given. To do a proof by contradiction, you take the prove part, right? I'm going to take this part right here, this part right here, and I'm going to assume the opposite. In other words, I'm going to say that the sum of m and n is odd, okay? And we also going to claim, we're going to let the reader know that I'm doing a proof by contradiction. So I say, assume, and it's always done this way, assume by contradiction that the sum, and negate this, the sum of m and n is even. Like I said, we like proof by contradiction when there's only two possibilities. Hey, the sum of m and n is either even or odd. There's no other option, right? It's either even or it's odd. All right, so assume by contradiction that the sum of m and n is odd, and the reason for that is called proof by contradiction. So here's your basic setup of a proof by contradiction. The rest is actually the hard part. The rest is I've got to take this assumption, ignore this, take this assumption and somehow get to some, I don't know, contradiction of a definition, contradiction of a theorem, contradiction of any statement that we proved in class. So let's see if we can do that. Well, the previous slide, which I just gave you, I defined an even number as 2 times k. So I've got two of them here. I got m and n. So I'm going to define that m is 2 times k, and n, since it's a different even number, I'll define as 2 times l, where both k and l are different integers. So m is going to be equal to 2k, and n is going to be equal to 2l. Okay, and that's how we're going to define those two even numbers. So that's just the definition of an even number. Okay, once again, what am I trying to do? I'm trying to find some contradiction. All right, here we go. Well, it says the sum. Well, the sum, therefore, will be m plus n. And since we just defined m and n as 2k and 2l, then their sum would be 2k plus 2l. So m plus n, by this definition right here, we're going to say is 2k plus 2l. Well, what allows me to do that? That's just plain old addition, right? Just add the two things together. All right, everybody with me?
Yeah.
Okay, no contradiction so far. I mean, this is good to go. Okay, well, the next step is kind of the key to the whole thing. On the left side, we got m plus n, and on the right side, we have 2k plus 2l. Well, if we remember back to algebra and factoring, notice both of these terms have a 2 in them, a 2 here and a 2 here, so I could factor out a 2. So in other words, I could just take the right side here and use a little bit of factoring and factor out a 2. Now, you may not know why I'm doing this, but clearly I haven't done anything wrong. There's no contradiction. There's no contradiction here. What allows me to do that? That's just factoring. Okay. Anybody want to take a guess what k plus l is?
Would it be 4?
Well, do you know what k or l is?
No.
No, we don't. Yeah.
We don't, but we do know that k and l were integers, right? So what's an integer plus an integer?
Another integer.
Another integer. Do we know what that is? No. But it's not going to be k and it's not going to be l, so I'm going to call it j, right? And what allows me to say that is because, well, I know what an integer plus an integer doesn't give me a decimal number. I mean, there's no way if I just limit you to the integers do you ever get to a decimal number. So I can conclude that j is an integer. So what did I do right here? Well, technically, I just added k and l. That's all I really did. The issue now is this. I mean, the issue is this right here. Literally, it says now 2 times j, and j is an integer. But how did we define even numbers?
A multiple of 2.
Well, we said it was going to be 2 times an integer. Hey, I just wrote it as 2 times an integer. But wait a minute. Our assumption was that the sum of m and n is
Odd.
And what did we just prove that the sum of m and n is?
Even.
That's a contradiction. So this was our assumption. Our assumption was that m and n were odd. We just did a little bit of, well, it was technically algebra, and we arrived at a contradiction. So we just contradicted ourselves. If m and n were odd, we could not have gotten to the fact that the sum of them is even, right? I'm sorry, if m and n were even, we could not have come to the conclusion that the sum of them is odd as our assumption stated. In fact, we just proved that they're even. So that's our contradiction. So our contradiction is this, the contradiction of this statement here and our assumption statement. So therefore, they can't be odd, they must be even. And remember, this works really well when there's only two. You can certainly use a proof by contradiction when there are three possibilities. You just got to repeat the process a couple times. So why was it a contradiction is because even numbers can be written as 2 times k, and we just wrote it as an even number, 2 times j, and we said that the sum was going to be odd, and that's not what we found out. We found out the sum was even. All right, so there is a example of an algebra proof by contradiction. So since we're in geometry, we should probably look at a geometry proof by contradiction. All right, we're only going to do 3 of these. All right, you might not get this one, but you should get the last one. So this is the one where it should kind of like click with you. All right. Once again, I'm gonna prove this by a proof by contradiction. A proof by contradiction. Well, the given stays the given. So we got a trapezoid. We got bases. The top and the bottom are our bases. It doesn't tell us what kind of trapezoid. We're trying to prove that the 2 bases are not equal to each other. SR and PQ are not. We're trying to have literature, which takes like 20 minutes. All right. So proof by contradiction starts with a given. Right? Starts with a given. And then what we do is we negate, or we write the opposite of our prove statement. So this is our prove statement. So we want to write the opposite of that. So what's the opposite of that statement? Someone?
PQ is equal to SR.
And unfortunately, I already clicked it, so you saw it there. Yes, okay, yes. So PQ is equal to SR, and I'm just going to make the statement to everyone, proof by contradiction. So when you're asked to write a proof by contradiction, this is what it looks like. The given stays the given, and your next statement is you take the prove part, you write the opposite of it, right? And the reason is proof by contradiction. So somehow this statement right here, that PQ is equal to SR, is going to, somehow we're going to arrive at some contradiction of some already known fact. Okay, so let's see if we can do that. Okay, I'll give you a hint. If you say that PQ is equal to SR, you can also say what?
SR is equal to PQ.
Sure, that would be the...
Or PQ is congruent to SR.
I like that one. We're going to say that PQ is congruent to SR. Good job. And that's just the definition of congruence. The fact that PQ is congruent to SR, well, we haven't arrived at any contradiction yet. We will. All right. I'm going to walk you through this one. What's the shape here?
Trapezoid.
What can you tell me about trapezoids?
I can tell you that if you add up the 2 bases, it will and divide them by 2, you will get the median.
Okay, there's something we could say. What else could we say? I wasn't expecting that one, Ben, but yes, you were correct. What else can you tell me about trapezoids? Just anything.
The top and the bottom are parallel.
Okay, I'm going to choose that one. Right? I'm going to say that PQ is parallel to SRY. Those are the bases. It tells us those are the bases. And we know that for trapezoids, the bases are parallel. That's by definition of a trapezoid. Okay? Now I'm going to reach way back into chapter, I think it's 4. What do you know? Trapezoids are quadrilaterals, yes?
Yes.
What do you know about these 2 statements? If you have a quadrilateral where the same side is both congruent and parallel, guess what you got?
A parallelogram?
You got a parallelogram. Right? This was, I had to look this one up. This is theorem 5.5. 5.5 says that if 2 sides of a quadrilateral are both congruent and parallel, then it's a parallelogram. Anybody see a problem with that statement?
It doesn't look like a parallelogram.
Oh, okay, a little bit better than that, but yeah, you're on the right track. Anybody see a problem with this statement?
PS and QR aren't parallel.
Well, we don't know that, but anybody see a problem with the statement that PQRS is a
A
parallelogram?
trapezoid can't be a
A
parallelogram.
trapezoid can't be a parallelogram, and we're told in the given that what's the shape that we got?
A trapezoid?
Yeah, we're told right here that it's a trapezoid. It's not a parallelogram, so we just contradicted ourselves. So the contradiction is that we're given that it's a trapezoid, and we just proved it's a parallelogram. There are no trapezoids that are parallelogram. There's our contradiction. So basically, our assumption that PQ is equal to SR cannot be true. So if PQ is not equal to SR, what is the only other option?
It's parallel to it.
Look at the statement.
Oh, wait, no.
If PQ is equal to SR, and we just proved that that's a contradiction, right? Then what's our only conclusion? Well,
That PQ doesn't equal SR.
I know, and you read it from right there.
Oh no,
The
my
mouse is giving me some problems here. But yeah, so if this is our assumption that was PQ was equal to SR, and we just proved that, well, that can't happen because PQRS is a parallelogram, and we know it's not because it's a trapezoid, then this assumption must be false. So if this assumption is false, if PQ is not equal to SR, the only option is, well, it's not equal. I'm not talking about values. I don't know what the values are. Therefore, we must conclude that PQ doesn't equal. And by the way, that's what it was asking us to prove. So here's another perfect example of where a proof by contradiction actually makes this a little bit easy. This would be more challenging proof to prove that PQ is not equal to SR using a direct proof. But by an indirect proof, we arrived to this, it took us 1, 2, 3 steps basically to get to an answer. All right, so there is 2 of 3. Now, where is the problem going to lie? The problem is going to lie is that you really kind of don't know the direction to go to get to a contradiction. You know what you want to do. You want to say somehow that this statement, PQ is equal to SR, is false because it arrives at a contradiction. But the question is, well, where do you look for that contradiction? Yeah, that's the challenge right there. Luckily for you, they're going to do some guiding for you to help you through this. All right, so QED. So the one that we're going to do as our last one is this one right here. All right, so I'm going to claim that you should be able to do this one without any help from me for the most part. So now you've seen 2 examples of it. I've actually talked about 3 with the dollar bill one. But now you've seen 2 of them, you should get a pretty good idea at least how the setup goes, right? McKinley, what's step number 1? What's my first step here?
Write down the given.
Okay, done. Anna, what's step 2?
The assuming.
Okay, so tell me what you want to assume.
That SR equals 6.
Okay, we're not going to do this part. We're going to do the prove part is that we're going to change.
Oh, so SP equals 3.
So we're going to assume by contradiction, right, that SP equals 3. We're doing a proof by contradiction. So this is always the second step. You assume that the proof part is opposite or false or whatever. You write that statement, and the reason will be proof by contradiction. Okay. So easy part is over. All right. Like I said, sometimes you have no idea where the contradiction will occur. So when that's the case, you typically go back to the given, and you just kind of go with the flow and see what the given states and try to say something that makes sense. So Ben, you got anything that makes sense that we could say as a statement? Just think out loud. Ben, are you still with us? Yeah, I can see you.
Yeah, I'm with you. I'm thinking.
I'll give you the hint. Look at the given. Just
Yeah,
say
I'm
something
looking
about
at
the given.
Well, if it's a rectangle, then SR if SR equals 6 and it's a rectangle, that means PQ must also be a 6.
I like that. I'll use that here in a second. Anybody else?
RQ has to be 3.
Where you RQ has to be 3. Okay, I like that. I'm going to use that. Anybody else? Let's see. We've used this. We've used this. There's one thing that we haven't used. What's the only part of the given that we haven't used?
The perimeter is 16.
So how could you say something about that?
I could say that SR plus PQ plus RQ plus SP must equal 16,
Okay.
which in better terms basically means SR, that number, but then it's not 16.
Oh, look at that, right? So if we, and by the way, we're just did some substitution in the fact that the opposite sides of a parallelogram or rectangle in this case are congruent. What were we going to say, Ben?
It's that right there. 16 does not equal 18. So
That's a pretty clear contradiction, right?
Yeah. So therefore.
So what allowed me to say 18 there? Just some addition or simplification. So therefore, we've arrived at a contradiction. 16 does not equal 18. If SP was equal to 3, then this would be a correct number. But since since this is a contradiction, therefore, what's our conclusion? If SP does not equal 13, what are my other options? I mean, there's an infinite number of options. SP
2,
2 or 5. So we can't really say what SP is equal to. We just know that it does not equal 3. Once again, this is back to a binary choice. If it tried to ask us to prove that SP equals 4 or something like that, that would be a harder thing to do. But this time, just to prove whether SP does not equal 3, well, it's pretty easy. Assume that SP equals 3, show that it doesn't, and therefore you know that it doesn't equal 3. So we're kind of done right there. That's a pretty easy one to do. So it contradicts our assumption that SP equals 3. We arrived at this logical fallacy right here that 16 equals 18. So there's another example of a proof by contradiction. The big issue here, and the one that it took us, even this one, and by the way, you guys pretty much did it by yourself. All I said was read the given and tell me something, and we eventually got to the right answer. So the issue here is, how do you know where to go to find your contradiction? And, at this level, beginning high school, proof by contradiction, start with the given and just bear fruit from the given itself. So just try to make logical, true statements about the given and see if that eventually reaches to some contradiction. Okay, any questions?
no.
So proof by contradictions, the idea is pretty simple. To do it, it certainly is. I mean, it's another game of logic, right? So I would assume that some of these will give you some challenging ones. If you got your book open, go ahead and open up. Let's take a look at page 216.
Okay,
I do have a question.
Yes.
Okay. So on the homework for numbers 7, 9, 10, and 14, it says write an indirect proof in paragraph form. Do you
It's up
really?
to you. I don't care if it's paragraph or
Two-column.
two-column. Either one.
Okay, yay.
All right. But yeah, so it's asking you. So I assigned you 7, 9, 10, and 14. Those are all the proofs. So 7, 9, 10, and 14. 14 is a bit more challenging, but they're all indirect proofs. Questions 1 through 5 simply want you to make that one statement, right? In other words, they want you to make this statement right here. The step number 2, assume by contradiction that SP equals 3. So all you're going to do on questions 1 through 5 is simply take the prove part, that would be the then part, and then write the opposite. So I'll do number 1 for you real quick for homework. So it says, if the measure of angle A is equal to 50, then the measure of angle B is equal to 40. So we would assume by contradiction that the measure of angle B does not equal 40. There's your first answer right there. Okay, so those 1 through 5 are pretty easily done. So give those proofs a good, you may not be able to get to all of them, but give it the whole night. In other words, you get stuck on one, walk away for it for an hour or two, come back to it. But see if you can get those proofs done. Questions?
No.
Okay. Proof by contradictions are really fun. Really fun. There's one other type of proof that we'll see later on in the year, but that will be it for types of proofs. All right, if there's no question, well, that's all I got for you today, guys. I will see you then tomorrow. Don't forget, everyone, make sure you're attaching pictures of your homework. Oh, I didn't talk about the quiz. So let me pull up, since you can't see it, let me pull up the quiz since I'm not sharing it. And I will tell you exactly what will be on the quiz. I pulled up the wrong one. All right.
Mr. C,
So the quiz is going to be on writing converses, inverses, and contrapositives. That's what the quiz will be on. Question, Allie?
No.
Anna? Whoever it was?
I do. So when we attach our homework, do you want us to attach the one that we corrected that day or the one that we did that night?
Well, hopefully you're not doing 2 different homeworks, right?
Yeah, but do you want us to do the one that we corrected in class?
I would prefer the one that you correct, right? So,
Okay.
but I also don't want you to, double submit that sort of thing.
Yeah.
I don't put homework in until I'm about to start it right now at the end of school is when I start putting homework in. So, yeah, and I also wait a day before I plug it in. So I'm not going to plug in today's homework today. I'll do that tomorrow. I'm going to plug in yesterday's homework into the grade book, and that way you have that extra day to get it turned in. Does that make sense?
Yeah.
Okay, cool. Well, I had nothing else for you guys. I will see you guys tomorrow then.
Okay. Bye.
Bye.